Hello everyone and welcome. Have you ever wondered why some things have vibrant colors while others don't, or how scientists can use light to figure out what a chemical is? The secret often lies in a tiny but incredibly important part of a molecule called a chromophore. Today, we're going to shine a light on this concept and understand why it's the star of the show in spectroscopy. The word chromophore literally comes from Greek words meaning color bearer, and that's exactly what it is, the part of a molecule responsible for its color because it absorbs light. Think of it as a molecule's personal antenna, specifically tuned to catch certain wavelengths of light. When light shines on a molecule, the chromophore is the region that can absorb that light energy. This absorption excites an electron, causing it to jump from a lower energy level to a higher one. The key is that it only absorbs light of a specific energy, which corresponds to a specific wavelength. The colors we see are actually the wavelengths of light that are not absorbed by the chromophore, but are reflected back to our eyes. For example, the beta-carotene molecule in carrots has a chromophore that absorbs blue and green light very strongly, which is why we see the remaining light as orange. So, what makes a part of a molecule a good chromophore? It usually involves a system of unsaturated bonds, like double or triple bonds. The real magic happens when you have a series of alternating single and double bonds, which we call a conjugated system. The more bonds you have in this alternating chain, the longer the wavelength of light the molecule can absorb. A small conjugated system might only absorb invisible ultraviolet, UV, light, making the compound colorless. But a very long conjugated system, like in beta-carotene, can absorb light from the visible part of the spectrum, creating color. This is precisely what scientists measure in UV-visible spectroscopy. The instrument shines a range of light through a sample and detects which wavelengths are absorbed by the chromophore. The resulting graph, or spectrum, shows a peak at the wavelength of maximum absorbance, known as the lambda max. This peak acts like a fingerprint, helping to identify the molecule and even determine its concentration. Sometimes, chromophores also get help from other groups called oxychromes. These groups don't absorb light themselves, but when attached near a chromophore, they can intensify the color or shift the wavelength of absorption. In essence, the chromophore is the fundamental reason for color and the primary target for analysis in many forms of spectroscopy. Thank you so much for watching. If you found this explanation helpful and want to learn more, please consider showing your support by liking this video, subscribing, or leaving a question in the comments below. Your support is what makes these videos possible. See you next time.